This is the simulation that students use for the forces and motion data collection and processing activity that is shown in both the student DCP Google site and the teacher DCP Google site. This simulation has got many different functions. For this particular DCP activity, we're just going to look at the friction simulation, but there are others that you can see at the top that you may choose to revisit with your students at another point. This DCP activity is particularly looking at the relationship between the normal force of the crate and the maximum friction force of the crate when a force is applied to it. To do this, students have control over these 5 sliders, and instructions are given to them in their verbal instructions. The first thing that students have control over is gravity. For this activity, we're going to set this for 10 meters per second squared to keep it constant. However, this being a reusable learning object, you could always come back and do another DCP activity where you change the gravity, say up to Jupiter, which will be what, 25 meters per second squared, or the moon going down to maybe about 2 meters per second squared. For the purpose of this one, it's always going to be 10 meters per second squared. The other thing that's also variable is static and kinetic friction. Students are given instructions that these two values are going to be the same. Therefore, these two numbers here should be set to be the same value at all times, even when they're asked to change the coefficient of friction. Students are told that we're not going to differentiate between static friction and kinetic friction, and they can assume them to be the same. However, you can always come back to this activity again at a later date and use this simulation to investigate the difference between the two. Students are also given instructions that object mass is the independent variable, and that they will be asked to manipulate or input different object masses due to the instructions given in the instructions sheet. Students are also explained that this value is shown here, and that they can take a suitable error from this value. That would obviously be 0.1 of a kilogram. Free body diagrams can also be attached to this investigation. The sum of the forces are also given to students, and that these should be clicked and the free body diagram should be shown, and positionality of the crate can be moved left or right. Personally, I like to keep it to the left. To find friction forces in this investigation, you're going to have to apply forward force. As soon as I apply a forward force, the friction force also starts to increase until we get an unbalanced force, or an F-sum force, and the object accelerates to the right. There's also a playback function at the bottom of this simulation, and if I clear this, as soon as I apply a force, you can start to see that the system starts to record. I'll get my F-sum force accelerated, moves to the right. If I play back this function, you can see that I can therefore look at force values I may have missed, or look at the free body diagram in more detail. For the purpose of this investigation, we're looking at the maximum friction force. That will be just the friction force just as the object starts to move. Hence, when the object is moving at constant velocity, we can assume that the friction force is the same as the applied force, and this is the friction force we wish to collect. To do this, students are instructed to reset the record value, move the object to the left, and apply a force just until the sum force appears, and then backtrack so that it disappears from the free body diagram. You can then assume that this box is agreeing with Newton's first law of motion, that the applied force is the same as the friction force, and that 299.77 newtons is the friction force that we need to record for this mass below. Finally, students are given instructions on the sensitivity of this force meter. This force sensitivity is to 1/100th of a newton. However, this applied force slider isn't. If you apply the force until the sum force appears, you'll see that just if you increase it slightly or decrease it slightly, that in actual fact it's not 0.01 of a newton, but 6.25 newtons. Students are given a hint that this sensitivity is not exact, but they're not told exactly this value, and they have to find it out for themselves. Students are also not told the error to expect here, and they obviously need to find this out for themselves. Therefore, the object mass will be 0.1 of a kilogram, and the normal force would therefore be ±1 newton. Thank you.